let me now get to the real business for this afternoon, for the last two talks of the day. And then, as we have been doing for all the different topics that have been covered during this conference, also now I would like to say a few words about the work of Bourgain in PDE, in particular dispersive PDE. So I was very lucky to be a graduate student at University of Chicago under Carlos Koenig around 1993-95. And around that time, there were two, I was considered fundamental papers that had been written in the field of, let's say, dispersive equation. So the two papers were the one by Bourgain, which many of you probably already read if you are in PDE. And if you didn't read it, to young people, you should read it. So the first is Fourier transform restriction phenomena for a certain lattice subset and application to nonlinear evolution equation, Schrödinger and KdV. And this was authored by Bourgain. And somehow the companion paper, more on the continuous setting, was by Koenig, Pons, and Vega, and is Wellposedness scattering results for the KdV equation via the contraction principle. Now, in my view, these two papers arguably were the fundamental ideas that really jump-started the work in dispersive PDE and started the incredible success that this field received in the last 20, 25 years. I will say that the fundamental idea, in my view, in these two papers is that when you look at the nonlinearity, you shouldn't look at it just as a product of functions with no structures, but if you are interested in a certain particular problems, let's say Schrödinger or KdV, and you are looking at the solutions of these equations, then the nonlinearity takes a very special kind of shape, and there are interactions, cancellations, and all of that can be exploited through a very fine harmonic Fourier analysis, and as Bourgain taught us in the periodic case analytic number theory. So I think that the interaction between analytic number theory and harmonic analysis Fourier analysis was well known to the expert, but I will say that there was Bourgain who brought it to the wide audience and community in the dispersive equation field. So we saw yesterday how this interaction and I would say reciprocal success of the two fields kept continuing since this work of Bourgain in the early 90s, and we saw yesterday, we witnessed that with both the work of Larry Guth and Cyprian Demeter. Now, while the Strickhart's estimates that Bourgain proved for the periodic case and the companion Strickhart's estimate that had already been proved and certainly improved since then were relevant in order to show that the solutions of dispersive nonlinear equations exist locally, the question of a global dynamics is much more complicated, and Carlos, as far as I know from the title, I think he will address some of these questions for the wave equation. And when you wanted to understand the global analysis, you have to know something about the system that keeps the dynamics under control. Clearly, conservation laws are extremely relevant for this purpose. And the very fine techniques and the estimates that were introduced since the work that I mentioned really helped in understanding the problem at the level of relatively low regularity given to you by the conservation law. But if you are even less regular than that, if you don't have a conservation law, then how do you understand, how do you control the global dynamics? And it was Bourgain that, again, introduced in our world of dispersive equation a tool, which I would like to call Gibbs measure, which can be defined, and have been defined before Bourgain for dispersive equations that have an Hamiltonian form. But it was Bourgain who used the invariance of this measure in order to control the dynamics and tell us that generically initial data in these very low regularity spaces still give us global solutions. And part of this will be the content of Andrea's talk. Now, I thought that I was going to say something original in my last remark, but actually Svetlana already said it, and many people before her said it as well. I think the remarkable, I would say kind of like a spell that the work of Bourgain has is that you read it, and you understand the idea after working hard, you're very happy, and then you go on and you publish your paper, and then you think you have another idea, and then you go check the work of Bourgain, and you realize that it's already there, with just the layer below what you are originally understood. And you can keep going for years, okay? And I'm not exaggerating when I say years. You can go back and read the paper again, you discover something new. I have to say that maybe this is also due to the fact that Jean makes sure that it's not, his papers are not written in the most pedagogical way, right? So there is the idea, there is the, and it, in a way, I actually think this is great because it really forces you to understand and then check that you're right. Instead of like, oh yeah, this makes perfect sense, and then you just don't retain it. So it would, like the blog of Terry said, it's exactly like that, very frustrating, but also exhilarating when you understand it. Okay, so I will conclude by saying I recommend it to all the graduate students here that if you want to find a problem to work on, just read Bourgain's books, paper, lecture notes, and so on. There are many of them, and good luck. So no, that's okay. No, you don't need to applaud for me. Keep it for the speakers. So the first speaker of the last part of today's conference is Andrea Nahmod. She's going to speak about long-time dynamics of random data, nonlinear wave, and dispersive equations.
I don't have this. Yeah. Thank you very much, Giuliola. And I would like to start by thanking deeply the organizers for the invitation. It's a tremendous honor to be here today. I just wanted to make a comment about what Giuliola says, that when we read Bourgain's papers, many times we feel like calling Eli and ask, do you know what he meant? I mean, it's like, but we think that Eli might know by now a lot of mathematics. I actually, sort of like many people have said, and they have spoke very eloquently about the impact of Bourgain's work. And like many of you, I have known of his work since I was actually a student. Certainly the work on the geometry of Banach spaces through Cora Sadowski, who was my undergraduate advisor, and so she explained me a lot of ideas in his work. And but I actually didn't meet him until 1997, 98. It was the first time I was here at the Institute. And I was then working on some problems on sort of a harmonic analysis questions of sort of these bilinear singular multipliers. And he was very interested in this, and he used to come to my office and sort of ask me questions that were related to his work on the pointwise ergodic theorems for arithmetic set. And he would ask me all these questions. Well, can you prove this convergence rate for your wave packet coefficients? And I was trying to finish my paper, but I couldn't stop thinking about what he was asking me. And I don't think that I could ever answer like what he wanted me to answer. I think these were open questions in his own papers. But there were many conversations like that, and he was very generous with his ideas and his time, and explaining, like, he even explained me sort of Gauer's work at the time. And then actually one of my favorite papers, which is a paper with Chypre and Demeter, Christoph Thiele, Rodolfo Torres, and Paco Villaroya, was inspired by some questions that Bourgain asked me that time. And I want to tell another story, which I think that tells you a little bit about the scale of things of Bourgain versus maybe some of us, which is that, like, the second time I was here was in 2003, 2004, when Carlos Kenny was the distinguished professor leading the program. And in one of the many seminars that we were here, Kaloshin was giving a talk about his joint work with Bourgain, which I think it was on sort of like Arnold diffusion for some Hamiltonian perturbations of sort of integrable systems. And so Jean was sitting in the audience, and so, he was very inquisitive about, he was trying to explain, I think, Jean, the part that he had done. I don't know if Kaloshin is here, but that was the thing. And so at one point, Kaloshin says to Jean, don't worry. I mean, if you spend 2 minutes on this, you'll understand what I'm saying. And so Giuliola and I look at each other, we laugh, and we wonder aloud, well, if it takes 2 minutes, how long it will take the rest of us? And he sort of was sitting in the front and kind of like hurt. And so he turned to us, and with a big smile and a winkle, he says, 2 years, and I think that he came short. I mean, with the 2 years, but I think that it gives you a sort of relative proportion of things and anything. So anyway, without any more, let me just go into the math. And Julia, you forgot your phone, but I hope it doesn't ring. The plan for the talk is a little bit, I'm going to spend a lot of time discussing Bourgain's approach, I mean, which is actually maybe starting from a paper in '94 on, so sort of the invariant gives measures and the notion of almost sure global Wellposedness for Hamiltonian dispersive PDE. And he did a lot of work, and I sort of going to mainly focus on a few examples on the nonlinear Schrödinger equation. And then it's sort of like, as I said, I'm going to spend quite a bit of time on that, and then I'll sort of like maybe illustrate some further some recent ideas on sort of this more probabilistic approach to Wellposedness, which is some joint work with Giuliola, which is more recent. And then finally, I will try to get into a sort of a new result, which we're still writing. So this is a sort of fairly new, which is actually joint work with Sahar Hani, Jonathan Mattingly, Luc Revelet, and Gilles Stafilani, in which we sort of like prove the existence and uniqueness of sort of a ergodic non-equilibrium invariant measures associated to NLS. And we are actually, I think that this is something that is very nice and that Jean would like very much. Anyway, so just to set a few examples, I mean, this is for those of you who know, this is the nonlinear Schrödinger equation, or the semilinear Schrödinger equation with the power nonlinearity P, and these two signs plus and minus are related to, I will say in a minute, to whether the equation is focusing or defocusing. And sort of the solution here goes from R into, could be any sort of, could be RD, the torus, or any compact manifold where you put here the Laplace-Beltrami. And I would mainly focus my talk on, after some preliminaries, on the torus case. And I mean, this equation has a rich structure, but I mean, let me just remind you that it has two conserved quantities, that means that things are constant in times, which is the mass and the Hamiltonian. And so you see the plus here corresponds to the plus here, and that's when the equation is called defocusing. And so what that means is that you see this Hamiltonian gives you control of the H1 norm globally. And if you have a minus, then this quantity may become negative, and you may develop blow-up. And I will leave maybe to Carlos to say more. This equation also, I want to say that unlike sort of a heat equation or diffusive equations, has time reversibility, so that means you can go solve forward or backward in time. And if you're on RD, then it has a scaling, which says that if you use a solution, the new lambda that scales this way is also a solution for the corresponding rescale initial datum. And from here, what you can see is that if you take the dot norms, the Sobolev, the homogeneous norms, then the relationship between the original datum and this is given by lambda to the to a number SC minus S, where SC is this number, d over 2d is the dimension, minus 2 over p minus 1, which is called the critical exponent. And so one way of, I mean, there are many things that you can do, but one way of classifying, the difficulty of the equation is according to whether I give you data for a problem in a Sobolev space HS, where the regularity of the data is above the critical one. In that case, you can see from here that then the scaling helps you, right? And so the scaling is your friend, and so the problem, you expect the problem to be more approachable. Then from here, when SC is equal to C, then if I give you data exactly there, the problem is called critical, and so then that's when the problem becomes a scale invariant, and so then you don't know what could happen. That's actually a much harder case. And then if I give you regularity, which is below this, then that's called supercritical, and then the scaling goes against you, and so you may develop blow up. I mean, but anyway. So, so a characteristic feature of sort of dispersive equations is the fact that different frequencies travel at different velocities. And so, I mean, and so if you're on RD, then this notion, which is encoded in what we call dispersion, gives you some decay of the solutions. And what the Strickers estimates are, which are a sort of a bunch of space-time estimates, which control, there are a priori space-time estimates controlling the solution, and encoding all this information, they are enough to somehow give you the theory, sort of the local Wellposedness theory, in most of the, in all subcritical regimes, and in some critical regimes, certainly for small data. Now, the question of long-time Wellposedness or blow-up is far, far harder than this and much more complex, and Carlos's talk will address exactly this question. So, so as Giuliana mentioned, in the last 20 years, there has been a lot of progress in the large data, not the small. So here I took small data is the Strickers, but the large data is much harder. And there has been a lot of progress, and essentially, certainly in subcritical regimes, there are essentially two methods that have been very powerful. One is the so-called high-low method that is due to Bourgain, that I think is from both of them are from sort of the mid-90s. And the I method of almost conservation laws that is due to Colliander, Kills, Tafilani, Takao, Katao, who from now on are going to be referred as CKSTT. So that's them. And these were actually quite powerful to actually obtain global results in subcritical regimes. But then it's like at the level of the energy, when in critical spaces, when the energy or the mass become critical, right, in which you're not in these regimes, then the problem is very hard, and then there has been quite a bit of work. I'm not being comprehensive with all references, but you know, this work on the sort of radial case from Grelakis and Bourgain, and okay, the CKSTT, Koenig, Merle, Tao, Kilipi, Zhang, Zong. And there's a particular very important method, or sort of that has kind of like been developed in the last few years. That started as sort of, we can find some of the ingredients here, but that it was further developed by Koenig, Merle, and also this with the focusing case, and that Carlos will tell you about. So despite all of this, there remain some important open questions in certain critical regimes when you are not at the mass of the L2, and especially also in the supercritical case where you don't even know if the defocusing case if you have blow up or not. So the story on compact domains on the torus is much more difficult, because then the way packets have no escape from interacting with each other, they will hit the boundary and come back indefinitely interacting. And so dispersion does not necessarily translate to decay. You have a limited dispersion, and what that means is that you lose a lot of the Strickers estimates, and you only have a limited number of them, and that survive. And these were the first ones were established by Bourgain in '93 in his GAFA paper, celebrated GAFA paper. And there was a conjecture as to the whole range and threshold of them. There was some work in between, but that finally was solved in the recent paper of Bourgain and Demeter. And so, in fact, actually what Bourgain showed is that actually the dispersion in this case is indeed weaker in the periodic setting. And he explicitly constructed examples, say, for example, for the L6 in 1D or the L4 in 2D, that actually show that you actually have an epsilon loss. And what that means is that that epsilon loss prevents you from closing the estimates. Say, for example, if you were in the quintic NLS in 1D or cubic, which are mass critical, that means that the SC is 0. If you are in RD, you can get a local Wellposedness, including including data in L2. But here you cannot, not even local. You cannot get this. And actually, to this day, the cubic NLS power 3 in L2 with data in L2 the local Wellposedness is an open problem. All right, so some of the sample of the results that were in that paper, in that GAFA paper of Bourgain, is here, as I mentioned. I'm repeating what I just said. That is, in 1D, the quintic equation. He actually doesn't matter if you're focusing or defocusing or focusing. Then the Strickers estimates he proved were enough to establish local well-posedness for S is strictly bigger than 0. So you cannot, this epsilon loss prevents you to reach L2. And the same for the 2D cubic. You have, in the defocusing case, local well-posedness for S strictly bigger than 0. Again, you cannot get 0. Okay, so these two problems at L2, they're open in the periodic case. Okay, local well-posedness, they're open. And essentially, once you have these results, I mean, if you take data which is smoother like H1, then you can, that corresponds to the conservation of the Hamiltonian, so then you can actually prove global well-posedness. And as I think that Giuliella mentioned a little bit, I mean, there were two fundamental tools in these papers which were actually groundbreaking, I should say. One is his proofs of the Strickers estimate on tori, which were not known. And the introduction of these sort of adaptive spaces where you perform a fixed point argument to get solutions, which is this sort of what is called the Fourier restriction XSB spaces or Fourier restriction method, which allows you to, is the place where you will perform a fixed point argument and get a solution. And actually, these were far-reaching, and actually they have had they were used a lot. Okay, so now how about global? So those results were local and global only if you are in H1, which is subcritical. So how about global at critical level, for which I have shown you that in the RD case you have a lot of results. Well, on the torus you have 1, 2, 1. That's it. There is almost no results. There is a result. The main results are, so for the quintic defocusing equation in 3D, this is energy critical, so the scaling is H1. So if you're critical here, the global well-posedness was established by Ionescu and Posader. This is large data, okay? By Ionescu and Posader in 2012. And previously, there's the work of Herzeg, of Tataru for small data. And a student of mine is sort of the 4D, which is an adaptation of that. But there is no more. Okay, there are no more results, global results, deterministic global results, okay, which is actually outstanding. I mean, it's very surprising, the contrast. And as I mentioned twice already, there is not even local well-posedness result here. So what we would like to do is we would like to sort of like change gears a little bit and say, well, I mean, if you don't have any deterministic results in here, then is there something that you can say from a non-deterministic point of view? And this was the point of view, although not for this reason, but this was the point of view that Bourgain started in sort of for Hamiltonian PD in 94-95, in which he actually studied the long-time dynamics for these periodic equations, dimensions 1 and 2. I mean, he didn't just did NLS, he also did KVV and actual other systems. From what we call the almost sure sense. Okay, so what he proved actually, and that was his main interest, is that the equation, which is what this means, the equation is globally well posed. So for a set of data of full Gibbs measure, I mean, the Gibbs measures were constructed before, and he proved his interest was to improving that is invariant. So what does it mean? What it means invariant is that you see you have a measure, these measures are constructed, and so the support live in some sort of Hilbert space or on some Banach space. You can put the support anywhere you want, but it has a certain regularity. And what invariance means that if you give me a measurable set, okay, and then you take you flow it with a nonlinear flow, then the measure of that set and the measure of the image of that set under the nonlinear flow are the same. So that's the notion of invariance. So it's kind of these two things are the same. And as I said a minute ago, the thing is the following. I mean, these measures were constructed before, like in the sort of for the cubic case. This is for the phi4 model of quantum field theory by Gliman and Jaffe, and there's other works that I'm not mentioning. And then in the context of Hamiltonian, where is work of Lewis, Ross, and Spears, and Zilkov. But this is just the existence, the construction of the measure. They didn't know if it was invariant. And the problem is that in order to prove that it's invariant, you first have to show that the nonlinear flow, okay, on the support of that measure is global. So if you don't know that you have global solutions for data in the support of that measure, then you cannot prove invariance. And so you can construct the measure, but the invariance needs this sort of global well-posedness on its support. And so why is it that this method works? I mean, why is the invariance so important? Because the Gibbs measures that you construct have support in like very rough spaces. They don't live in the typical H1 or L2 spaces. They are like in rougher spaces than those. But what they do if you have the invariance, they act as a conserved quantity at a level of regularity where you don't have a conservation law. And so the invariance of this measure is used in lieu of a conservation law to continue a local solution into a global one. And that's kind of the key. Okay? And so, and the other virtue of the Gibbs measure is that in some generics, it sort of captures generic behavior of a flow. And there are certain things that you can say, but let me not digress now. Okay. So there's, of course, sort of challenges and limitations of this method. And so let me mention a few. Actually, one is the actual existence in general for dispersive equations is the actual existence and invariance of the measure. As I said, for NLS, this was known. And then actually proving the global well-posedness on the statistical ensemble of that measure. If you are on sort of bounded domains, they're easier to construct than on infinite volume. That's actually it's a different question. And they are not available in higher dimensions. Here I want to be a little bit more graded in what I say because I want to explain this a little bit better. So if you are in dimension 1, you can construct them, no problem. If you're in dimensions 2 or dimension 3, and you are dealing with the defocusing cubic NLS, then that's exactly what comes out of the work of Glimm and Jaffe in the 70s, that you cannot construct such a measure unless you sort of renormalize the potential part of the energy. So you have to do a renormalization of the potential energy for this measure to exist. And in 2 dimensions, you can actually do something more than cubic. You can also do other powers. You still have to do this renormalization, which is some people call it weak ordering. And in 3D, the renormalization is much more complex than the weak ordering, and it only works for the cubic equation. So for example, if I give you, instead of the cubic equation in 3D, I give you a quintic, a power, then there is no Gibbs measure. I mean, what people know is that there is no such a thing. If you try to find such a renormalization, you will either go to the trivial measure or to a Gaussian, but you will not get a Gibbs measure. And also, for example, there is no Gibbs measures in 2D for the focusing case. In 1D, yes. And there is, if your dimension is bigger or equal than 4, then there is also none. Okay. And the other point is that actually, if you have a PDE that is not Hamiltonian, then how to go through this process of almost sure global well-posedness and invariance of the measures is much more complicated. All right, so these actually are 2 problems which I think that, I only put them here because I think that this is opening a window into a lot of current research, and there is a very exciting time to be talking about this. And so I'm just going to put it out there because I'm a proponent that, it's always good to talk to other communities. And so, as I said, if you are in the defocusing case and you take the quintic in 2D, then there is a Gibbs measure. And as I said a minute ago, if you're cubic in 3D, you also have a big Gibbs measure. But what's the problem? The problem is that when you look at the support of these measures live in very, very rough spaces for which there is not a well-defined flow. Okay? You cannot prove any estimates, and there is not a well-defined flow. And so proving their invariances, if you cannot prove some sort of global well-posedness, is a problem, and in these days a challenge. But there is actually some hope in that the recent developments, I think, in the stochastic PDE world, especially people doing sort of para-control distributions and sort of regularity structures like Gubinelli and Hare have introduced sort of like new tools that I think our community is looking at that could shed some light into these questions. Okay. So let me review Bourgain's work for the quintic because I want to illustrate a little bit how is it that it worked. So I'm going to take the focusing case because the focusing case, this is what is in the paper of Lewis, Rosen-Speer. This was the case that they constructed. And then the Hamiltonian explicitly has this form. So it's the kinetic energy minus the potential energy. And I'm going to call the potential energy like n of u for nonlinearity. And actually, the L2 is also conserved, so I'm going to modify this, and I'm going to abuse notation and call it still h. I'm going to modify it and add the mass into here. And I'm only doing this because I want to avoid the problem at 0 frequencies. And so what you want to do is you want to think of u of t as sort of an infinite dimension vector, which is given by its Fourier coefficient. So this is the Fourier coefficients of u of t. And so think of your equation, your PDE, as an infinite dimensional Hamiltonian system for these coefficients. And so what Leibowitz, Ross, and Spear, what they did is they considered the Gibbs measure, they actually constructed, and I am writing this formally. Formally, that measure is given like this, like, the expression that you will think this is the exponential of minus the Hamiltonian times what it should be the Lebesgue measure. And what they prove is that this measure is actually a well-defined measure on HS in one dimension, provided that S is strictly less than a half, but not at a half. And why is it that I say that this is formal? Because actually none of these terms, none of these factors here make any sense, right? I mean, this is kind of like, it's a suggestive way of writing it, but all the terms involved in this expression are infinite. So how is it that this measure is defined? Well, what you have to do is you have to start with a reference measure, which is the Gaussian measure. So you want to start with this Gaussian measure, and once you have these Gaussian measures, you construct the Gibbs measure as a weighted measure in 2 steps. So the first step is to construct the Gaussian measure, the infinite dimensional Gaussian measure on HS as the weak limit of the usual sort of finite dimensional Gaussian measures. And I want to recall you that then for this rho n, which is a finite dimensional measure, then you can view it as an induced probability measure on, say, R4n plus 2, under the map that sends omega into these terms, where G and N are sort of IID complex Gaussian random variables on a probability space, so omega is in omega. And so the point now is that then you know that this rho will be the weak limit of those rho n's, but what you would like to do is you know that this rho is easily additive, but what you want is to be countably additive. But in order for this rho to be countably additive, you have to check the trace of certain Bessel potentials in here. And actually what you get is that then it's actually this can be realized as a countably additive probability measure, provided that in one dimension your regularity is strictly below a half and not above, and not here, you're with probability 0 here. In 2D you have to be below L2, okay, and dimension 3 you have to be below minus a half, so you see you kind of lose half a derivative as you go up in dimensions, so you become worse and worse and worse. And that's going to determine, if you wish, where is the support of the Gibbs measure going to live. It's going to live in these regularities on these dimensions, okay, so remember those numbers. And of course, then rho also yields for phi a distribution of a random Fourier series, which is almost sure a function if you're in 1D, but if not, it's a distribution. And you also have sort of the tail estimates, the usual for tail estimates. So once this has been constructed, then one constructs the Gibbs measure sort of as the measure which is absolutely continuous with respect to the Gaussian measure, and whose Radon-Nikodym derivative is exactly the potential, the exponential of the potential part of your Hamiltonian. And this is the renormalization. And the point is that because you are in the focusing case, the only way that you can renormalize actually this measure is if you put an L2 cutoff. I mean, if you were in the defocusing, you don't need this, but in the focusing, you need this. And for the quintic, this B has to be sufficiently small. All right. So that's for the construction. So now let's look at the theorem. What is that Bourgain did? I mean, he says, okay, now I have this measure. I want to prove that this measure is invariant. I have to prove that then if I take an element, the typical element now in the support of this measure is going to look like this. Then I want to prove that then I have a global flow. And indeed, that's what he proved. He proved that there exists a set of full measure 1, his measure 1, which is inside h½ minus, which is where the support is, such that for any such initial data in that place, the initial value problem is globally well posed and the measure is invariant. And again, let me repeat this, what I said before, that is that deterministically, Bourgain had proved that you have local well poses above 0, and global about H1, okay, from conservation Hamiltonian, right, small L2. And here what you're doing is you're using the invariance of the measure to extend this to sort of to extend the sort of the local solutions that you know that if you are in H1/2 minus, you have deterministic local solutions because the half minus is bigger than 0. But then you don't know that you can extend them past the local time, and that's what he does thanks to the invariance of the measure, although there is no conservation loss, and he still can do that. He can control the growth of the solution. That's what the measure does for you. And so how does he do this? And this is actually this is what maybe Bourgain brought at the table. He says, well, you know, you take you have to first look at the finite dimensional approximation of your Hamiltonian PDE, and he does that by taking, you can do other things. I mean, you can do Galerkin if you want, but this is for harmonic analysis. This is better for the estimates. So you take this Fourier projection into frequencies less or equal than n. So you look at the problem, you solve this problem, you take the data, you project it, okay, into frequencies less than n, and now you solve this problem for that data, and you call that UN. And as I said a minute ago, we already have a deterministic local theory, so I know that I don't care that this has Van Green domains. I can completely ignore this omega, ignore these random variables here. This is still a function which is, you know, in H1/2 minus. So I have local Wellposedness above 0. So this I have a deterministic local theory in 1D. And so what that tells me is that there is a time that is independent of n on which this problem has a local solution. So far so good. So what's the crucial fact now? The crucial fact now, and this is what is hard for other equations, especially when you have to do sort of gauge transformations and things like that. But the crucial fact is that you see, you start with the Hamiltonian equations and you do the Fourier projection of this, and you don't know that the solution to this projected finite dimensional approximation is still satisfies a Hamiltonian. That is still a Hamiltonian system. And in this case, it is. Okay, so that's the point. That in this case, this is still a Hamiltonian system. And that the Hamiltonian for this, which is still this, is still conserved under the finite dimensional flow. And this is absolutely crucial. So what that means is that if you look at now this measure, this finite dimensional measure, which I call mu n, which is nothing but the exponential of the Hamiltonian of the finite dimensional solution times this, which is a finite dimensional Lebesgue measure, then Liouville's theorem tells you that this measure is volume preserving, you're in Hamiltonian structure, and this is conserved. So that means that this measure, this finite dimensional measure, is invariant, okay, under the flow of the finite dimensional system. And this is all you need, because this is actually something that I want to emphasize. That's all you need. The invariance of the infinite dimensional measure comes at the end, as the icing of the cake, after you have proved global Wellposedness. At this stage, in order to prove the almost sure global Wellposedness, all you need is the invariance of this measure, of the finite dimensional one. And indeed, what he does is he uses the invariance of this measure to actually extend UN to sort of to find what he calls a good set of initial data. So it's that if you have drawn from omegas from a good set, then you can actually extend, use the invariance of the measure to extend UN from a local solution to a global one. Okay, that's the invariance of the measure. You extend the finite dimensional solution, the solution to finite dimensional problem from local to global. Okay, and now what? So now what you do next is you do a second step, which is you prove an approximation lemma that tells you that a little bit maybe in a rougher topology, the UNs converge to U. And so then how is it that you extend the U? U exists locally, and I want to make it reach time t. So what you do is you say, well, I'm going to extend UN, and then I'm going to walk the U with me one step, and then I'm going to extend the UN again, and then I'm going to walk the U with it, and I'm going to carry it with me thanks to this approximation lemma. And this approximation lemma is not entirely trivial. Because you cannot compare U and UN directly. You need an intermediate system as a stepping stone, and maybe I will not explain it. But as I said, it's not entirely trivial. Okay, but once you have that, these are the two ingredients that you have to conclude the theorem. Okay, then you still have to prove that this mu n converges weakly to mu and that mu is invariant, but this is kind of like pretty standard after you have these two things. So now let's look in 2D, and Bourgain's work in 2D came maybe 2 years later, 96, I don't know, I mean, probably it was published in 96, I don't know when it was done. But he said, okay, let me look at the measure now, at the Gibbs measure. He was interested in proving the invariant of the Gibbs measure, which existed for the cubic equation in 2D. Now, as I said a minute ago, in 2D, from the work of Glimm and Jaffe, you know that this measure doesn't exist if you take the cubic, the Hamiltonian, the phi-4 model. So the Hamiltonian, the potential is the power 4 of u, that you need to do some renormalization. And actually, in his work, this renormalization arises also naturally, and I want to show you how, okay? Because they are connected, and they're connected from completely different points of view. Okay, so let's see. So the problem that you actually can solve is not this, but is, what's happening here, is this. So what you do is you need to somehow renormalize the nonlinearity by subtracting. Okay, this is a little bit of abuse of notation. You need to do the finite dimensional approximation, and then you subtract sort of the expectation of this, and okay, times 2. But anyway, let me write it like this. You subtract this term from the nonlinearity, because this is actually a bad term. It's a bad resonant term, in the sense that you will not be able to prove the multilinear estimates you need. Whenever you have, here you have 3 functions, so if you take the Fourier transform, it's a convolution, you have 3 frequencies, and if a certain pair of frequencies become equal, then this term will collapse into something that is like this, which is linear in U. And if it's linear in U, then you have troubles. I mean, and I'll show you in a minute. And so now you take data which is like this, and now if you look at this data, and you are in 2D, then this data is below a half, because this converges if you are in below L2, sorry. Okay, so you are now in H minus epsilon. The cubic equation in 2D is a scale invariant in L2. So this was the first ever result where there were the existence of global solutions in the supercritical regime. Okay, this is a 96 paper. And essentially what he did is he said, yes, then I can prove that then the solutions of these are almost surely global well-posed, and the associated Gibbs measures are invariant. And here I try to explain a little bit why you need to remove this term. The problem is that if you look at this term in the kinetic energy, then when you're trying to construct it, then this is unbounded almost surely, and so you need to sort of do this renormalization, which is called weak order, that essentially produces that term. All right. So there is an additional difficulty in this problem, which is that now in 2D, the only local well-posedness you know, deterministic, is above L2. And I want to solve the problem below L2. So now I don't have a local, he didn't have a local well-posedness to jump-start the process. This is what I said before. You have a local well-posedness, you use the invariance of the finite dimensional Gibbs measure to extend the solution of the finite dimensional problem to a global one, and then you do the approximation lemma to sort of extend the infinite dimensional one. Here there is no jump starting, there is no local well-posedness, deterministic, that you can do. But then his point or his observation is that, okay, but look, I mean, you don't need to prove a deterministic local well-posedness to start. All you need to show is that you have well-posedness for this data. That, in other words, that you need a probabilistic local well-posedness. That if you take data of this form, okay, I don't need to prove it for every single data here. But I only have to prove that if you give me random data of this form, then I have a local solution. So in other words, the point is that it's enough to prove a probabilistic local well-posedness for sort of the typical elements in the support. In other words, for random data, phi omega in H minus 2. And this is a 96 paper. The paper, I can't remember how many pages it has, maybe 50. Okay? Okay. 48 are to prove this. 48 papers are to prove this result. The rest, once you have this, his observation is that once you have this, what I just explained you a minute ago can be put into place, and you can finish. So why is it that random data then helps you? Okay, what's the point of the random data, and what was Bourgain's strategy, which, by the way, is actually in the stochastic community they use, in the sort of the Prato-Debush community, they use the same trick. So it's the following, right? So randomization does not improve the regularity of a function. So if you have a function and you randomize its Fourier coefficients, then that's not going to improve the regularity. But what it's going to do for you is going to improve the LP properties or the LP integrability almost surely, which in turn implies better estimates than the one that you have deterministically. And so this goes back to sort of all results on random series. Sort of go back to Rademacher, Kolmogorov. I mean, this is actually a pretty well-known fact. And Bourgain's strategy then was that what you want to do is you want to look for solutions of the form, the linear evolution of the random data plus a W, where W will satisfy the difference equation. So in other words, you don't look for solutions U, but you write U as linear evolution of phi omega W, and you use the fact that the linear evolution of random data has almost sure better LP estimates to prove that this W, which is written in this form and solves this equation, okay, actually is better, lives in a smoother place. Okay? And then on the side, you also need a deterministic local Wellposedness in a smoother space. So in other words, you start with phi below L2, and then what you're going to prove is you're going to prove that the solution to this problem, W, is going to land above L2. Now, when you do that, the problem is that don't think that solving this means that you're going to do a fixed form argument in a space that is above L2, and that's all, that you become subcritical. Because you have here a nonlinearity, right? So you have interactions of things which are rough but random and smoother and deterministic, and you have to treat interactions of random with random terms, deterministic, and mixed terms. And the mixed terms are the usual ones, the ones that give a lot of trouble. And so as a consequence, he proves something that is quite remarkable for sort of in general for dispersive PDEs, because this is actually not something that is that easy to prove or that you expect for all of them, is that almost surely in omega, then the nonlinear part is smoother than the linear part. Okay? And this is just what I just said before, that you have to be careful. So the tool that you use in all of these things is sort of this sort of large deviation estimate, which I guess that people here know. But I want to tell you why is it that you use. So here you have a sort of some sort of linear combination of sort of like N1 through Nk Gaussian sort of IID Gaussian random variables and some coefficients. And then the theorem, the large deviation, tells you that then for any p bigger than 2, the LP relative to omega, the LP norm of this is bounded by the L2 norm. Okay? So that's the typical estimate. But the point is that then from Chebyshev, you know that then the probability of the set of omegas where the absolute value of fk omega is bigger than some lambda decays exponentially. Okay? And so now if you choose your lambda, say this number doesn't matter too much, okay, forget this number. So if you choose your lambda to be the L2 norm, then directly what that would allow you is that says that, well, if I exclude a set of omegas, okay, with probability 1 minus this number, I will be able to replace in my estimates the absolute value of square by the norm, the L2 norm square. And that's crucial. Okay, so let me show you why. Here's an example. So take this data. I forget the square root of 1. I just forget any 0. This is the same as the square root of 1 plus n squared. And let's look at some typical term that you will have to evaluate when you are trying to control the all random terms. So when I'm trying to prove an estimate, the nonlinearity is just 3 terms. You have 3 functions, and they're all random. So if you look at one of the things that you have to estimate, what you're going to see is that you have to estimate the little L2 in n and the little 2 in m, a norm of this function. Okay, where here is what this set is the n1, n2, and 3, such that n1, this comes from the convolution. And the fact that n1 and n3, these two, are not equal to n2 is absolutely crucial to keep these things independent, and it's exactly what the weak ordering gives you. So even if you didn't know the work of Glimm and Jaffe, you will be forced here to actually remove these frequencies. Okay? And so now, if you were just to do Cauchy-Schwarz here, so if you write what this term means and you just do Cauchy-Schwarz, then you see that what you do is you pick up the size of this set. You have to count, these are integer lattice points, you have to count this set, and you will pick that set, the measure of that set here. And when you want to close, you cannot close because this number is too big and it translates into a loss of derivatives. So what you do is you don't want to do that because that's silly. That's ignoring the fact that you have something random here. So you use the large deviation estimate, and what I just told you is by, okay, outside, except for some small set of omegas, you can replace this by the L2 norm. And once you replace this by the L2 norm square, you use the independence to get this. So you see no more that term. And once you are here, you have enough decay to close and do your estimates. But that's the key. So to summarize, when deterministic statements about existence, uniqueness, stability are not available, what we want to do is we want to sort of turn to a more probabilistic point of view and investigate sort of these problems from a non-deterministic point of view. And this is actually particularly nice sort of for supercritical problems, but also for problems which might be subcritical, but there is a gap in between what's known on the local Wellposedness and the global Wellposedness, or the almost sure Wellposedness and the deterministic Wellposedness. As I said before, randomizations are used just to improve the local theory. So this is actually, maybe I should say this again, which is what comes out of Bourgain's work, is that the randomization of the data allows you to improve the local theory, and then is the invariance of the measure that allows you to prove that, to say that you can go from local to global. But there are two different things, okay? And so the randomization techniques have been used quite a bit, and not just for sort of dispersive PDEs. And then in many of these problems, if you're not in NLS, you don't have a sort of like on higher dimensions, you don't have invariant measures available. And so you have to, how do you go? You use randomization to improve the local, but then how do you go from local to global? It's a different story. And in some cases, like on the wave equation or so things like Navier-Stokes, you can use energy methods. There is also work on sort of probabilistic adaptations of what Bourgain high-low the I method is. And anyway, so that's so there has been a lot of activity since Bourgain work in the last. So nothing happened actually since his work until 2007, 2008, when this topic was retaken, and since then there has been a lot of activity. And I'm going to just flash something very quickly for you. 1 second. So it's a lot of equations, a lot of name, a lot of people. If you're interested, I can show you later, but let's move on. So, so here what I want to discuss is I want to discuss now in the last maybe 15 minutes or 20 minutes, I can't remember. I think I started 20, for 20, no? Okay. You made it 55, okay, whatever. So I'll finish. I only have like, what? 9 transparencies. So, all right, so the first thing is that what we wanted to do with Gigliola is we wanted to see, in light of the work of Ionesco and Posader, in which they have the critical, large data critical Wellposedness, global Wellposedness on the torus in 3D for the quintic equation, that's H1. We wanted to see first if we could actually obtain the analog of the local Wellposedness of Bourgain. This paper that I told you that he spent, 48 of the 50 pages in 2D for the cubic, to see if we could actually do something for the 3-dimensional quintic equation. And actually, the differences were Bourgain are non-trivial. I mean, okay, first of all, you have a quintic nonlinearity, which increases the complexity of the interactions and estimates you have to do. So that's just kind of like maybe bookkeeping. So, but there are many more cases and that you have to do. The second one, which is actually very, very important, is that actually in all these methods, even when you have the new Strichers, even when you have all the new Strichers that were established by Bourgain Demeter, there is always some sort of basic analytic number theory that you have to do. You have to do some sort of like integer lattice counting on spheres or intersections of spheres with balls, and you have to have good estimates, and these estimates are very nice, maybe in 2D, but when you go higher dimensions, they degenerate, they are less nice. And actually, this is one of the reasons why, for example, for irrational tori, we don't know how to do these things, because then instead of spheres, and that's for him, it's ellipsoids. So anyway. So anyway, and the other difference is that here there is no measure available, and there are no conserved quantities for the difference equations, so how to obtain global for a full probability is not clear. And so what we can do with Gigliola is, maybe before I do that, is essentially we can actually carry over this thing and obtain the almost sure local Wellposedness. And for the large data, for the long time, we cannot prove that this is true with sort of probability 1, but we can do it on a positive probability set. So in other words, what we can show is that there exist some infinite energy solutions which are global, okay? So in a probabilistic sense, okay? And the second result is this probabilistic propagation of regularity result that is new that we have with Joriola that is actually is quite nice, and is so essentially what it does is it closes two gaps in the theory. One is in the 2D case for the cubic equation. So let me try to remind you what happened here. So Bourgain proved almost sure global Wellposedness in H minus epsilon. And then I think that's coming in the next transparency. So I'll show it in a minute. Okay, let me just maybe state it here. Then I go to the next one. So we proved two things. One is the almost sure global Wellposedness in 2D for the cubic here. So this is now going not to the supercritical, but again going above to more regular solutions. And then we also proved that in 1D, if you are focusing, you can go above a half. So you may be wondering why we are going into more regular, and the reason is because there was a gap here. And so I'm going to try to explain this gap in the 2D case. So Bourgain proved for the 2D that you have almost sure global Wellposedness in minus epsilon. Here you have 0. And then there is deterministic results, which are by, where is it written? There, by the Silva, Pavlovich, Stavilani, and Tsirakis that say that if you are above 2/3, you have a deterministic global Wellposedness. And that was done via the I method. And so now what happens is that you said, well, what happens between minus epsilon and 2/3? If you were in the deterministic setting and you have a result, say, in L2, but you have a global Wellposedness in L2, then there is a standard method which is called preservation of regularity that tells you that if you differentiate the equation, essentially you can, once you have the global Wellposedness at the level, say, of L2, then you have it for anything smoother. In the non-deterministic case, that's totally false. That you don't have that. If I have Bourgain's result at the level of minus epsilon, that tells me absolutely nothing about smoother data, okay? Because with probability 0, my random data is going to be in the support of the measure. So I cannot do that, and I cannot differentiate the equation. It doesn't work. And so, so that's what I wrote here in this remark. So our idea was to suitably decompose the data. So it's a little bit, it's actually very, I think it's a very, very general argument that you can use in general for other equations, is that what you do is you decompose the data that you have into a term that is in some suitable topology, which is the rough topology, close to the statistical ensemble of the measure, to the terms for which you have Bourgain. And then you have a remainder, which is actually, you can make it a bit smoother, and that you could presumably eventually, after a little bit of work, use deterministic arguments to treat. And then in order for this to work, actually, you have to actually make this more precise, because you need to actually see why it works in the, I don't have transparency, but why this thing of this approximation, this closeness to the support of the measure works. And there is actually what we call a non-deterministic perturbation argument that is close to conclude. And so in general, what it says that, well, look, I mean, if you have some sort of global Wellposedness result at this level, let's say that this is rough level, and it was obtained using the invariance of the Gibbs measure, not by other methods, but by the invariance of the Gibbs measure, then if you give me anything that is to the right, that is a smoother, I cannot do the regular propagation of regularity, but this argument tells you that you can actually still get it, and you can. So we close these two gaps, and that's it. All right, so let me actually, in the last few minutes, talk about this, another question that is actually very close to Bourgain, and that he did a lot of work, which is this notion of sort of a transfer of energy or energy cascades, and sort of what is the something very hard for NLS, which is the out of equilibrium dynamics. So if you want to think about this in very general forms, all of these things about Gibbs measures deal with sort of like maybe sort of the equilibrium case, and now we're interested in the non-equilibrium case. And so if you are on RD, then by now we have a lot of results for which you know that after you have scattering, which means that after sort of long enough times, the dispersion sets in and your solutions have like a linear behavior. And if you're linear, then the energy, or which could be kinetic energy of the mass, while remaining conserved, does not move its concentration zones from the low to the high or from the high to the low. In other words, there is no, for the linear, there is no forward or backward cascades. And once you have scattering, then that tells you that then the solution to the nonlinear problem is going to also avoid these cascades. Okay, so on RD, you have some of these results. But if you're in a compact domain, these results are sort of like lost. Okay, you don't have anything like that. And you expect this out of equilibrium dynamics. And so the question is how to analytically describe this expected out of equilibrium behavior, and which is also from the physics community. Is also called weak turbulence, and I'm not qualified to talk about that, so I'm not going to talk about it. But it's related to the Kolmogorov-Sakharov spectrum. I don't want to sort of talk about that. But anyway, so what was Bourgain's approach to this trying to quantify or to try to understand these cascades, or this sort of a migration of the energy to higher frequency? And the idea was that he wanted to, the approach was that you should study how the higher Sobolev norms grow. So if you prove a result at the level of H1, because H1 is conserved, then the norm, if you have a solution, will not grow. But if you give me something smoother, even if I have a global solution, then in a smoother norm, the norm will grow with time. And if you do the silly argument, it will grow exponentially, for sure. And he did work in which he improved these upper bounds. But here the question is not about the upper bounds, but about the lower bounds, okay? Whether you actually do grow. And so if they grow, then that will give you a quantitative estimate of how much of the support of U hat mod square has transferred from low to high frequencies while maintaining the mass and the energy constant. So some of the first works on this were by Bourgain and Kusking, and actually Bourgain constructed explicit sort of a perturbed 1D nonlinear wave equations that exhibit this energy transition. And actually, he got sort of this power-like growth. I mean, he did some work. And then after that, I mean, he posed this question in which says, so the question is a conjecture that is known as the unbounded orbits conjecture of Bourgain, or infinite cascade conjecture, which says, well, does there exist global solutions to the cubic NLS whose HS, this is a very smooth norm, okay? I mean, this is not about, assume you have a solution, and that's not the issue. And it's very smooth, so, but do you have them so that they grow indefinitely in time, such that this is infinity? Okay? So the fundamental progress on this question came from work of Colliander, Kiel, Stafilani. Okay, I didn't put CKKSTT, but okay. Colliander, Stafilani, Takao, and this work of Sacher-Hani also, Patrick Jarre and Grelier, Guarde Kaloshin. And so let me tell you a little bit what the CKSTT did. It's like what they did is they constructed a large by finite growth of the Sobolev norms, and the result is as follows. If you give me any small delta and any sort of large k, then they were able to construct a solution to the cubic equation in 2D, okay, and find the time such that you can start infinite, you can start very small, and then at that time you will surpass that k. So there's no rate, but it's showing that you have this growth, this migration. And more recently, I mean, there is work of Hani, Passader, Tsetkov, and Vigiglia, in which instead of the torus, when they look, as soon as they put an infinite direction, which is R, like a non-periodic, then they could solve this problem. So let me actually quickly tell you about this, and I will not have time to get into the proof, but so this is joint work with, as I said, Hani, Jonathan Mattingly, Luc Borrellier, and Gigliola. And so we were interested in somehow an intermediate, you could think of this as an intermediate thing about the two things that I have just spoken. One is the Gibbs measures, which is kind of the equilibrium, and the sort of these unbounded orbits things. And something in between these two problems is actually the study of the existence and uniqueness of non-equilibrium invariant measures, okay, which has interest in its own right. Now, this is actually a very hard problem at the PLD level, even for stochastic system, but there has been recent work in which people have been trying to answer similar questions for sort of ODE systems that model the heat transfer on a chain of oscillators. And so the work by these people, but more recently by Hare and Mattingly, in which they took a chain actually of 3. Remember that number, 3. Number 3? three anharmonic oscillators with a very simple, the classical Hamiltonian, sort of just the nearest neighbor coupling. And they put those two into contact with two heat baths at different temperature. And they were able actually to model this non-equilibrium dynamics. Okay? And so our point of departure is the work of CKSTT. And they have in this work that I just said, they come up with sort of something they call a toy model that is related to sort of the resonant NLS, and whose Hamiltonian is given by this. And this Hamiltonian is much harder than the one that I just mentioned of the sort of anharmonic oscillator, because besides having sort of like nearest neighbor couplings, you also have sort of to take into account momenta. Okay, so you have to take into account the momenta of your neighbors as well. And so this is much harder. And what we do is we take the first mode and the last mode, and we attach them to heat baths to different temperatures. So what we want to do is we want to take the system, a finite dimensional ODE system, and we want to inject energy. That means we want to kick the system by injecting energy in the low mode and have a lot of dissipation in the other mode, so that the energy sort of there's a flux of energy. And so this is kind of like a standard stochastic method to add dissipative energy. The control waves, and so the system looks like this. So here, this is a Brownian motion, and so T1 is much less than Tn, and so you see this is what we do. We put this in the lower mode, and then this Tn is much larger, so this is the dissipation, and here this is the Brownian motion is kicking energy. And in the middle modes, we don't touch them. And so if the first thing that you can prove is that if T1 for this model, if you are at equal temperatures, that's back to equilibrium. Okay, and we prove that then the Gibbs measure, there's a Gibbs measure, and it's an invariant, and it has that form. Okay, that's not hard. But the interesting question is exactly this one. If T1 is strictly less than Tn, does there exist, we want to know, does there exist a unique smooth ergodic non-equilibrium invariant measure? And the expectation is that then that should be, because an initial distribution of the system should sort of converge to a non-equilibrium state in which this energy is flowing. And the answer to this question is yes. And we have to also take a chain of 3. So here, all this n should be 3. Where is n? I lost n. Okay, so there's only 2 here. There's no here, nothing here. So we take 3 of them. And with 3 of them, we can answer this question and do this construction. And maybe in 1 more minute, 2 minutes? 1 minute. Yes, one. I want to say that this is much harder because it's the first time. So what is hard about this problem? The ergodicity or the uniqueness is not hard. The hard part is the existence. Is how do you prove that this measure exists? In order to prove the existence, you have to construct a sort of a Lyapunov functional that for the system that satisfies this. Okay. So in other words, what you want to do is you want to say that there is some sort of a compact set, a region in phase space where most of the dynamics spend your time, and you have to construct sort of the Lyapunov function that tells you that you're constrained there. And the usual candidate for this that people take, I mean, these are very hard to construct by hand, is just some sort of coercive conserved quantity of the original Hamiltonian, like e to the m. M is sort of the energy. But this doesn't work here in the whole space. This is the problem with this problem. The problem is that in order to find this Lyapunov function, you have to break this phase space into 4 difficulties, and it's very difficult to construct. You cannot guess it, and so you have to actually solve a sort of I'm going to show you a picture, maybe here. So you have to. This is the last one, So if you put here this E1 and E2, the i's. The i's are kind of like the square of the c's. So it's the square is absolute value of C1 square, absolute value of C2 square, so on. That's M. And so you have this region here, right? And so the problem is most of the dynamics should occur there. And then the problem is that you lose hypolepticity when I2 is 0. So, but you have hypolepticity everywhere else. And then the point is that you want to construct your Lyapunov functions that tell you that as soon as you enter those regions, you come back here immediately. And so you can guess some of them by hand, but you cannot guess them all. And also you have to match them at the boundary because they have to be, you need something that is continuous. Okay, they are C2 inside and continuous. And so in order to do that, you have to actually do a very delicate study of sort of the phases. I mean, how you need to understand that in some regions the phases lock and they give you what you want. And in other cases, you have to actually explicitly solve a Poisson kernel, a Poisson equation for the effective dynamics and this. Okay, sorry. Thank you very much.